Okay. I assume that you guys have watched the video that I sent last week, and let us see a little bit more on data analysis and statistics. I believe that you have learned statistics previously during your A-level, matriculation, STPM, and so on. All right. So about the data analysis, we have heard a normal phrases in describing result of analysis. If you have an analysis, we normally say pretty sure, very sure, most likely, probably, right? But it is not an accurate answer for data analysis. We have to replace using the statistical test, okay? And it's important to understand the significance of the data and therefore to set limitation on each step of analysis. And we have to know that there are errors in chemical analysis, right? And I believe that you have identified what kind of errors that we have learned during the video last week. Okay, systematic errors. Okay, what else? Please, I want you to open your mic and respond to my question. Okay, so that I know that you are there. Okay, what kind of error do you have? I have named one, systematic error, and what else do you have?
Personal error included.
What?
Personal error.
Okay, personal error is included in what type of error? Random error, systematic error?
It's random. It is random.
Pretty sure? Are you sure about that? Let us see after this, okay? So impossible, is it impossible to eliminate errors? Okay. Actually, we are not, no, it's quite impossible to eliminate errors, but we can reduce the errors, right? And what is the maximum error that we can tolerate? Can only be approximated to an acceptable precision, right? So also we have to know exactly about what is accuracy and what is precision. So accuracy is a degree of agreement between measured value and a true value. In case we have a true value, okay, so we have to measure how much the agreement, degree of agreement between the measured value and the true value. For example, we have a standard, okay, a standard material. Okay, sorry. Let me open my video. Okay, let's say we have a standard material that have a specific concentration of any analyte inside it. For example, we just name it just metal, heavy metal. For example, mercury. So we have, for example, a standard that have 10 ppm of mercury. Okay, so and then we measure the value by our method. Okay, in our lab, okay, for the mercury content. And then how much the agreement of our analysis, the result of our analysis with the true value. Okay, let me annotate. Okay, so this is how to differentiate between accurate and precise. Okay, look at this one, the first one. Okay, let's say the true value is the yellow circle. So it is very accurate, okay, because close to true value, and also precise. Most of the result that have been analyzed is close to each other. Okay, so it is precise. Okay, let us look at the second photo. Okay, this one. Okay, what is your comment about this photo? This is a true value. This is a true value. Okay, and the analysis of the sample, the result is, you know, not it's quite close to the true value, but it is accurate. Is it accurate, guys?
No.
No, not
No.
accurate.
No.
All right, because it is not as similar as a true value. Is it precise?
Yes.
Yes,
Yes,
precise.
because the result that we have done the analysis, the result is close to each other, right? Yeah, but this is not accurate. What about the third photo? Is it accurate and precise? What about your comment?
Accurate,
Not
but not
precise, but
precise.
accurate.
not precise because the result, okay, uh, is not close to each other, right? But some of the result are within the true value, which is accurate. And the last photo, what is the comment, guys?
Not accurate, not precise.
Yes, not accurate and even not precise. Okay, very bad analysis, right? Meaning that a lot of errors have been, occurred during the analysis of this sample. If we stay with the example that I told you, we have a known concentration of mercury inside the sample, 10 ppm of mercury. But look at the analysis, not even close to the true value and also not even precise. The value of the result that have been analyzed for the sample is not close to each other, right? So not accurate and not precise. Okay, inaccurate and imprecise. The precision. Right. Okay. Next. What is this? Okay. All right. Oh, I can on the subtitle right now. Let me test. Hello? Can you see it? All right. So the precision, okay, the degree of agreement between replicate measurements of the same quantity, repeatability of a result. Okay, the degree of agreement between replicate measurement, we have a replication of analysis, and the value of the replication is close to each other. And expressed by the standard deviation by the coefficient of variation, the range of the data, or as confidence interval 95% about the mean value. How similar are the values obtained in exactly the same way and also useful for measuring deviation from the mean? Okay. Welcome back, guys. I don't know what happened to the internet just now. Can you hear me?
Yes, doctor.
All
Can,
right,
doctor.
good. Okay, let us continue. Okay, so the precision is about how close the result from each other and expressed by the standard deviation. Okay. This is another example. High precision and high accuracy. Guys, can you hear me? Please respond.
Yes.
Yes, doctor.
Okay. All right. So high precision and low accuracy, you can see there. Low precision and low accuracy, and low precision and high accuracy. So which one do we want for our analysis? Which one do we want for our analysis? Of course, high precision and high accuracy. All right. So accuracy is expressed in terms of error. The first one is systematic error. Okay. Determinable, and that presumably can be either avoided or corrected. Can be constant. For example, uncalibrated wig using all wigging, and variable. Example, burette whose volume reading are in error by different amount at different volumes. And reading all too high or too low, that can affect accuracy. And how to detect the analysis or reference sample or determine recovery after adding known standard. Okay. So what is recovery? Okay. After we done some of the analysis, okay, we measure the result of, we just put a known concentration, all right, of material, and then we analyze, and how close our analysis, our analytical result. For example, we just stay to our previous example, 10 ppm of mercury. Let's say the recovery, okay, this is the recovery. After we analyze the 10 ppm of mercury contained in the sample, how much do we analyze? For example, we got 11 ppm, not 10 ppm exactly, we got 11 ppm. So how many percent of the result that we got deviate from the actual value? So this is 11, meaning that it is 110%, right? Am I correct? The 100% is 10 ppm, but we got 11 ppm, so that this is 110%. So the recovery is 110%. Or if we analyze a 10 ppm of mercury that contained in a sample, we got 9 ppm. So the recovery is 90%. Okay. So the acceptable value, please take note. Okay, guys, please take note. The acceptable value for the recovery is plus minus 20%. Meaning that, let's say the example again, 10 ppm of mercury. If we analyze, then we got 12 ppm or either 8 ppm. It is in the range of acceptable. Why? Because the acceptable value is plus minus 20%. If it is low, 20% the actual value, it is acceptable, and it is high, 20% from the exact value, also acceptable. So plus minus 20% is acceptable. More than that is not accepted. Okay, so it is globally, internationally accepted that recovery must be plus minus 20%. Okay, understood, guys? Recovery. So what is meant by recovery? Okay, meaning that when we analyze samples or a lot of samples that we analyze one by one, and then we must analyze a sample that with a known concentration to test our recovery of our method and also instrument. If it is within plus minus 20%, so our method instrument is quite okay for the recovery. If it's more than that, for example, for the 10 ppm of mercury, we got 15 ppm. So the recovery now is more than the plus minus is more than 20%, which is more than plus 20%, more than 20%. 15 ppm is 50% more than the actual value. So this is not accepted. All right. Or if we analyze 5 ppm for the 10 ppm of mercury inside the sample, it is also not acceptable more than 20%. Okay, the value is plus minus 20% accepted. We got 5 ppm. So this more than acceptable value for recovery because it's the amount of the mercury is less 50% from the actual. All right, understand, guys? Understood? Please, if you understand, please thumbs up about the recovery. What is acceptable value for recovery, guys? Again,
Plus minus 20%.
yes, good. Okay, plus minus 20%. And now we go to random accidental or indeterminate error. Okay, some of you guys or Rushaidi told that the human error include in the random error. Okay, so what is random error? Represent experimental uncertainty occurred in any measurement, random and cannot be avoided. Okay, it will affect the precision and can only be controlled and also can be controlled and revealed by small difference in successive measurement made by the same analyst under identical condition. And it can't be predicted and estimated, but can be dealt with statistic. So data scattered approximately and symmetrically about a mean value. Okay. Stop annotate. Oh, sorry, what's this? You can see my mouse. Where is my cursor? Okay. Right, then we have gross error. Okay, before that, let us see the figure there. So this is systematic error. Okay, it is precise but not accurate. Okay, but if you have random error, so it is not precise nor accurate because of the unpredicted error. Okay, unpredicted error. See there, very far from the actual value and also not even precise. Right, and then we have gross error, serious but very seldom occur in analysis, usually obvious, give outlier reading, detectable by carrying out sufficient replicate measurement, experiment must be repeated. For example, what is that? Instrument faulty and contaminated reagent. So it is from the gross error. We can consider it as the gross error. If instrument faulty and contaminated reagent, it will fall under the gross error. Okay, now we must see some example there that by your own self. Okay, systematic error. You understand systematic error, determinable and can presumably can be either avoided or corrected. Uncalibrated weight and also uncalibrated instruments. As for example, the burette hose volume reading are in error but different amount at different volume. Okay, what else? Another example that you can give for the systematic error. If you understand, you can give some example of that. If you want to use instrument, you must calibrate it. Okay, guys, again, recall how to calibrate the instrument. For me, I taught you AAS. Okay, to how to calibrate AAS. Again, please. If this question will be asked during the final exam, then it will be easily answered by you guys. So how to calibrate the atomic absorption spectrometer? Come on. Hello? Suddenly, no people talking. Suddenly, no response. Oh, I didn't open my camera. All right. You guys can see me. All right. So, guys, please. Okay, Tan Jizang, Tai, can you open your mic? Just speak about it. How to calibrate?
Using one blank sample plus 5 different concentration
All right.
to obtain the calibration graph.
All right, good, Tai. Thank you so much. Okay, we prepare a blank and also 5 different concentration, increasing concentration, and then we plot the calibration graph. Okay, remember my class, I've told you all instruments are, let me hear the keyword. I told you. All instruments are, guys,
Not clever.
not clever. Okay. So we need to teach the instrument. How to teach the instrument is through the calibration plot. Okay, we prepare, we told the instrument, this is blank. Okay, no analyte inside. Instrument, this is 1 ppm. This is 2 ppm, 3, 4, 5. And then plot the graph. Okay. So if the result fall within the calibration plot, we can measure the concentration. Okay. Because the instrument only detect the response or the what we call that as yes, response. For example, AS is the absorption, right? And then translated into the concentration that have been told by us, the analyst. We the one who teach the not so clever instrument. Understood, guys?
Yes,
And
doctor.
all right, good. And then I have told you about one more type of the calibration, that if we have a matrix that can disturb the analysis of the sample, it is especially for the AS or any spectroscopy instrument, then we prepare the calibration solution and we add what? Remember, if we have a sample that have a matrix that can affect the analysis, we do a type of calibration. We prepare a series similar. We prepare a series of different concentration of analyte, but we add a similar volume of what inside the 5 different concentration of solution. We add what? Remember that? We add a similar volume of sample itself. Remember that? I think you have done also in your lab for AS, right? Come on, guys. Recall back. What we call that method? What do we call that method?
Addition method, doctor.
Standard addition method. And then after that, you plot the graph. It will cross the x axis at the negative side, right? And the overlap of the x axis is the what? The overlap at the x axis is the concentration of the analyte, but you need to put it in positive. Remember that? The standard addition? Guys, remember? Okay, good. All right, now, systematic error is about uncalibrated instruments, right? Mostly about uncalibrated apparatus, right? That may be cause the systematic error. It can be determined, okay? And then we have a random or accidental error. This one we cannot determine, but we can know through the statistic. Okay. Yes, like Rushaidi say, this is it is by human error. Okay, because the data are scattered. Okay, approximately. All right, and then we have a gross error. It is very rare and seldom, but also occur. Then we know this is about instrument faulty and contaminated reagent. Okay, this is the example of the gross error. All right. Now, instrument error. All measuring apparatus contribute to systematic error. Okay. And also we have method error due to inadequacies of physical or chemical behavior or reaction. Okay. And also we have personal error. Now, instrument error that we know, instrument error are in systematic error. What about method error? Method or error also include in systematic error. Okay. It is difficult to detect and the most serious systematic error. If you analyze, you analyze with a wrong method, then it is a very serious systematic error. Okay, that's why for every analysis, the first thing that you need to do is to refer to the what? Refer to what? Recall back.
Standard method.
Yeah, standard method. Okay, that we have learned the standard method. Okay, and then we have a personal error. Okay, personal error include in the random error. Okay, handicap, physical handicap, insensitivity to color change. You have color blind. Okay, when you transfer the solution and some of the solution spill, right? Incomplete drying, math error in calculation. That is the personal error. Right now, the application of statistic in data analysis, okay, in defining the confidence interval, the range of value around means within which the population mean can be expected with a given probability. Okay, and then determine the number of replicates to assure at the desired probability, and also estimating the probability that the experimental mean and true value are different, or two experimental mean are different. We have a different test here. The most famous one is t-test. Okay, we estimate the mean and the true value of the sample. Okay, also we have the probability that the data from two experiments are different in precision, that is Ftest. Okay, and deciding when to accept or reject outliers among replicate, that is the Q-test. Remember these three tests. Okay, if we have a known value of a sample and then we do a test, okay, then we estimate the probability of the experimental mean and the true value are different, or two experimental mean are different, then we have to choose t-test. Okay, and then if you want to estimate the probability that the data of two experiments are different in precision, we have two set of data from different experiments. Okay, and we want to measure either both experiments have different in precision, then we have to do F-test. And deciding when to accept or reject outliers among replicates. Okay, we have a result of analysis, and most of the results are close to each other, precise, but one of the result is outlier. Okay, different from all the others. Okay, then we want to decide that we want to accept or reject the outliers among the replicates. So we do the Q-test. Okay, statistical treatment of a random error, the sample mean divided by the average. Okay, if for large data set, it is called population mean. Okay, it's mu. But for small data, right, small data set, it is just sample mean. So xi representing the individual values of x, okay, the sum of individual value of x, okay, and then divide by the number of the set, number of replicates of the measurement, okay, and the range, the difference between the highest and the lowest result, that is we call as range. What about the median? The data in the middle of the number is odd, arranged in ascending order, increasing, okay, and then the median is the middle one. For even numbers, the mean of the median pad is used. If you have a even numbers of replicate, then we use the mean of two middle, a pad of middle replicates. Then we just take the mean. If the series of replicate is in odd number, we just take the middle one. Used when a set of data contains an outlier. So errors, absolute error equal to measured value, okay, deduct the true value, okay, and relative error is the absolute error expressed as percentage of the true value, okay. For example, negative 0.1 gram, okay, divide by the true value 2.72 gram times 100%, so the error is negative 3.7%. And then we have standard deviation. Okay, you have know about this standard deviation. Each set of analytical results should be accompanied by an indication of the precision of the analysis. The standard deviation, which is measuring of the precision of the population of data. So standard deviation always represent the precision. Okay, how close the data from each other. Okay, this is the example, small size sample. N equal to 20 and population is N larger than 20. This is the equation for the standard deviation. Just use Excel, then we can calculate it. Okay, variant. The square of the standard deviation is the variant. Okay, and also we have relative standard deviation, also a very important precision indicator. Okay, the standard deviation divided by the mean times 100%. So acceptable RSD percentage depend on the type of analysis. Okay. For example, for the trace analysis, RSD percentage should be less than 5%. For environmental analysis, should be less than 15%. And for the pharmaceutical analysis, it should be less than 10%. Right, this is example of HPLC chromatogram of toxins. We have replicate 1, replicate 2, and replicate 3. Okay, can you guess which result with higher precision? I think the link is not there anymore. It's okay. And confidence limit and confidence interval. How sure are you? Okay. The calculation of SD for a set of data provides indication of the precision inherent in particular procedure. If for large data set, it doesn't by itself give any info about how close the experimental determined by the mean and to the true value. Okay, statistic allows to estimate range within which true value might fall within a given probability defined by the experimental mean and SD. This range is confidence interval, and the limit of this range is confidence limit. Okay, normally you know about how much is confidence interval and also confidence limit, and have been asked in the question, right? Let us see the example. Okay, this is the value of the confidence level. Okay, and the degree of freedom. Okay, 90%, 95, and 99. Okay, normally we use 95 Okay. Example, data for the analysis of calcium in rock are given by 14.35%, 14.41%, 14.40%, and 14.32%, and also 14.37%. Within a range, are you 95% confident that the true value lies, right? The confidence interval equal to mean plus minus TS divide by square of total number of set. Okay, the solution is mean is 14.37. The standard deviation is 0.037 from the data table at 95 confidence interval level, and minus 1 is 4. So T is 2.78. Where is it? Okay, this one is the T value. Okay, we have N is 5, so it is need to minus 1, and then the minus 1 is 4 at 95%, 2.78. Okay, therefore the confidence interval, okay, after we put inside the formula, okay, equal to 14.37% plus minus 0.05%. So you are 95% confident that in the absence of the determinate error, okay, the true value falls within 14.32 to 14.42. How you get it? 14.32 to 14.42. How you get the value? Okay, this is plus minus 0.05%. Okay. At different confidence interval, okay, we try at different. So at different 90%, so the confidence interval is 14.37 plus minus 0.04. 95, just like we calculate previously, and 99 plus minus 0.08. Summary, if the confidence interval level increase, if the confidence level increase, the confidence interval CI also increase. The probability of the true value or the true mean value mu appeared in the interval with increase. All right, so that is about the confidence interval. And then we have another example there. Okay, now we close to 10 a.m. 5 minutes more. You can see other example of confidence interval. Okay, now we want to see about t-test. Okay, I told you we have 3 types of tests: t-test, an F-test, and Q-test. Okay, for t-test, comparison between experimental mean and the true mean to check the presence of systematic error, and can be used to compare replicate measurement, and also can be used to compare individual difference. So step into t-test. The first one is comparing two mean values, right? X and also mu. If sigma, what is sigma, is not known, okay, then we have, so what is sigma, guys? What is sigma? We have two things, okay? If sigma is not known and if sigma is known. So we have two different calculation here. Okay. Okay, then the second step is calculate T or Z, the T calculate value from the data, and compare the T calculate and T table. If T calculate is larger than T table, we reject the null hypothesis. Okay. So mu is not similar to x. The difference is due to the systematic error. So we know that there is a systematic error occurred in the analysis. If the t calculated lower than the t table, so we accept the null hypothesis. Okay, so mu is equal to x. The difference is due to random error. So random error, okay, is detected if the t calculated lower than the t table. So we just see the example here. The sulfur content in a sample of kerosene was found to be 0.123%. A new method was used on the same sample and the following data, okay, is obtained. No, the first thing is the sulfur content of a sample, know that 0.123%. Okay, a new method have used to analyze a sample and got this series of data. So we want to know either this new method have an error or not. So whether the systematic error is present in the new method, the null hypothesis is the mu equal to x. Right? So x is equal to, you just calculate the mean. Okay? The mu is the true value. Okay? X is the mean. 0.116%. Mu is 0.123% here. Okay? You got mu from here. True value. Okay, and S is 0.0032. What is S? You calculate the standard deviation. So the plus minus t equal to x minus mu. Okay, and then square root of n. Okay, what is n? 1, 2, 3, 4. 4 set of data. Divided by S standard deviation here. Then you got the t calculate is 4.38. And from the t table, okay, at 95% confidence level, n minus 1 is 3. The t table is 3.18. Okay, so guys, can you accept the new method? Since the t calculated is lower than the t table, so hypothesis is rejected and the two means are significantly different, and thus systematic error is present in the new method. Okay, so now we know. The next question is, the ash content in a sample of coal was found to be 0.923% using a STM method. Okay, this is a standard method, right? So when you see that in the question, they said already that it is using the standard method. So this is the mu. This is a true value, the mu. Okay. Another new method was used on the same sample and the following data is obtained. So this is a new method that have been developed. Okay. So this is mu. And you calculate the x, the mean. Okay. And also the standard deviation. Okay. And then show whether systematic error is present in the new method. Use 95% confidence level. I have told you that normally they use 95% of confidence level. So at 95% of confidence level, how much is the t table? Okay. First, we calculate the n. Oh, what happened to my cursor? All right. 1, 2, 3, 4. N minus 1 is 3. So 3, 95%, 3.18. All right. And then next. Okay. The null hypothesis is we accept the new method. Okay. So mu equal to x. And then we calculate x. Mu there. Mu is here because using standard method. Okay. And then we calculate s. Put into the formula. So we got the t calculated, and then the t table is 34.18. So t calculated larger than t table. So what happened? Since t calculated, t calculated is lower than the t table. So since the t calculated lower than t table, hypothesis is accepted and the 2 means no difference and systematic error is not present. We can accept the new method. Understood, guys? This example of
Yes,
t-test.
doctor.
All right, good. Now next, the concentration of an additive in a standard sample of gasoline was measured 5 times with the following result. Okay, 0.13. This is a percentage of by mass. Okay, right? Okay, 0.13, 0.11, 0.12, 0.20, and 0.14%. Okay, so this is n. 1, 2, 3, 4, 5. N equal to 5. Okay. And then if the accepted value for the standard sample is 0.11 using SR, this is a mu. So mu is 0.11. Are the result for this set of measurement be significantly different? Okay, at 95% of confidence level by t-test. So now directly, okay, you know, they want 95%. So you can get the t table already. Okay. Okay, and then you calculate the t value. So how? The null hypothesis, okay, you just write the null hypothesis is mu equal to x. So calculate x. You got x, you got mu here. And so f, standard deviation. Calculate the t calculated. So t calculated is lower than t table. So if lower than t table, let us see. Of course, if lower than t table, hypothesis is accepted and the 2 means no different and the systematic error not present and the method can be accepted. And more example we can see there in the notes. I will upload the notes for you guys just after this lecture. Okay, now comparing two means value. Sorry, okay. Normally used to determine whether the two samples are identical or not. Sorry, okay. Let me identify the nodes. Okay, this is still in t-test. Okay, so you can also compare the two values of x1 and x2, two methods. Okay, the difference in the mean of two sets of the same analysis will provide information on the similarity of the sample or the existence of random error. Okay, if you calculate, okay, and then sorry, okay, the data x1, x2, and s1, s2, we just calculate from the two sets. Okay, then the hypothesis is both mean are equal, and we want to test the x1 minus x2. X2 is 0, meaning that is equal. So the similar t-test equation, the t equation. Okay, we have two here, set 1 and set 2. Okay, and then we just assume mu1 equal to mu2 and sigma1 equal to sigma2 and calculate value of t. Okay, so how the t calculated become like this? Okay, because of what? Okay, because of this one. Okay, and also the assumption of mu1 equal to mu2. So the equation come like this: x1 minus x2. Remember, this is special for if we compare two sets of data. Okay, two set of data. Either random error is there or not. Okay. All right, and then after we calculate the t value, and then we compare to the t table. If the t calculated lower than t table, okay, of course, hypothesis is accepted. Okay, So the pool standard deviation SP is calculated using this formula, where N1 and N2 are numbers of data in set 1 and set 2. Now let us see the example. Okay, urine sample obtained from a patient was determined for arsenic content using ICP-MS conducted in 2 different labs. Okay, this is how they compare the t-test. Okay, these t-tests are compared for 2 set of data. So now we have the situation of between 2 labs. All right. So lab 1 6 determination. So mean is 12.61 ppm. Lab 2 4 determination. So x2 equal to 12.53 ppm. And the SP is 0.07 ppm. Prove that both urine source are different. So what is SP, guys? Again, the pool standard deviation. Okay, now we assume that the hypothesis is set 1 is equal to set 2, meaning that no random error. Okay, but we have to prove using the T calculated must be lower than T table. So T calculated, okay, the formula for T calculated is x1 minus x2 divided by the pool standard deviation and times by the square root of n1 and times n2 divided by n1 plus n2. So after we put all the values, okay, 12.61 minus 12.53 divided by 0.07 times 6, okay, times 4 divided by 6 plus 4 equal to 1.7. And from the T table, at the 95 confidence with the degrees of freedom 6 plus 4 minus 2 equal to 8. Okay, why 6 plus 4 minus 2? Refer back. Okay. Okay, remember, we need to deduct 2 because we have 2 set of data. Okay, for the T table, place minus 2 to find the T table because we have 2 set of data. So we plus both of the number of n and we minus 2. So we got 8. So we find the 8 from the T table and we got 2.31. Now, since T calculated is lower than T table, so hypothesis accepted and the source of the urine statistically is the same. So we can accept from both lab, the result from both labs. Okay. Right, value of confidence level. Okay. Now we go to Ftest, comparing the precision of 2 measurements. Is method A more precise than method B? And also, is there any significant difference between both methods? Okay. Yes, we have some confusion between Ftest and also the t-test for comparing the 2 mean value. Okay, now we look what is the difference. The Ftest is used to compare the precision of 2 measurements. Okay, not not to compare if this one, okay, to compare identical or not to compare the identical, meaning that the result is identical or not, that we are using t-test to compare the identical of 2 means of a data set. But for f-test, it is used to compare the precision of the measurement of 2 measurements. Okay, is the method A more precise than method B? Remember, for f-test the keyword is precision. Guys, if you understand, please thumbs up. This is important to differentiate between t-test, okay, and also f-test. The t-test we have 2 types, right? The first one, okay, we want to compare the series of data from the true value, the known value. For example, they give the result from the method that have been referred to the standard method, ASTM, so on. And also we have a 2 set of data to compare, is it identical or not. But for F-test, we want to compare the precision of 2 measurements. Method A more precise than method B or not. Is there any significant difference between both methods? Okay, so this is the formula of F. Do you remember the V the variance is equal to the standard deviation square. Okay, so we have two set of data, f equal to v1 divided by v2. So it is s square for s1, s1 square, and divide by s2 square. Because variance is standard deviation square. With a degree of freedom n minus 1, hypothesis is the precision is identical. Okay, so set 1 is equal to set 2. Method A is equal to method B. Okay, like that. Okay, if the calculated f calculated lower than f table, of course, like t-test, okay, the hypothesis is accepted. Okay, we have the numerator and denominator. Since the value of f from table are always greater than 1, the smaller variance, okay, the more precise always become the denominator. So v1 larger than v2, so f1 is larger or similar than 1. Right, f value in the table. Okay, now we have example. The determination of carbon monoxide in a mixture of gases using the standard procedure gave us S value of 0.21 ppm. Okay, the determination of carbon monoxide in the gases using the standard procedure give S value of 0.21 ppm. The method was modified twice, giving S1 of 0.15, 10 degree of freedom, and S2 0.12, 10 degree of freedom. Are the two modified methods are more precise than the standard? Look at that question, right? The solution is, the hypothesis is S1 is equal to the S standard and S2 also equal to S standard. Okay, calculate one by one. So F1, we calculate the F value, and F2, we calculate the F value. So 0.21 divided by, okay, so for the question that already told the standard, so you just assume that the standard is the nominator. Okay, remember this one, since the value of f from table always greater than 1, the smaller variance, the more precise, always become the denominator. Okay, and then s standard square divided by s1 square. Okay, we got 1.96, and f2 here, f standard square, or the variance square, or the variant of standard divided by variant of set 2. So we got 3.06. Now, in the standard method, standard deviation to sigma and the degrees of freedom become infinity. Refer F table. So the numerator is equal to infinity, and the denominator equal to 10, giving the critical F table. F table is 2.54. How they got it? Here, 10 degree of freedom. Okay, so F table is 2.54. How they get it? 10. Okay, and how they got 2.54 here? Infinity. Okay, okay, how they got S sigma and the degrees of freedom become infinity? How they got infinity value here? Because we want to we want to refer to the F table, the degree of freedom, the numerator. How we got the infinity value here? Guys, you have any idea how the degree of freedom for the question is decided as the infinity, the numerator? We have denominator and numerator. The the denominator given there is 10. Okay, but how they decide that the nominator is infinity? Okay, normally if they say that in the standard method, okay, in the standard method here, using standard procedure, okay, s value 0.21. So in the standard method, s is close to sigma, and the degree of freedom become infinity. Okay, so normally if we use standard method, so just assume, okay, the nominator, okay, for the standard is infinity. Okay, so the numerator is infinity and the denominator is 10 here. Okay, the numerator always become always from the standard. Remember this statement? Okay. Since the value of f from table are always greater than 1, okay, of course, look at the table. The f value is always greater than 1. The smaller variance, okay, the more precise. Always become the denominator. Meaning that the new method always become the denominator. And the standard method must become the numerator. And numerator for standard method normally, okay, infinity. And the numerator is 10. Given the critical, f table is 2.54. So, since f1 is lower than f table, so hypothesis is accepted. And f2 is larger than f table, so hypothesis is rejected. The conclusion is S1 is equal to the S standard, okay, the precision, okay, and S2 is not equal to S standard. It's not precise. Okay, now we go to the next test, which is a Q test, a way to detecting an outlier. Okay, what is outlier? A data that does not belong to the set. Okay, for example, we have a set of data 10.05, 10.10, 10.15, 10.05 again, 10.45, and 10.10. We know normally from the data we know this one is the outlier, 10.45, but we need to do a test. By inspection, 10.45 seems to be out of the data normal range. It is easier to see when the numbers are arranged in the decreasing or increasing order. At 95 confidence limit, should this data be eliminated? If the data 10.45 eliminated, the mean will change from the original value. Of course, when we reject one value, the mean will be different. So, the Q experiment there is the equation where SQ is the questionable data, XN is the nearest neighbor, and W is the difference between the highest and the lowest value. Okay, so the Q experiment or Q calculated will be compared with the Q critical or Q table and check the hash null or the hypothesis. This is the Q table, right? All right, so the Q experiment we can calculate here xq minus xn divided by w. Okay, then we got 0.75. So from the Q critical or Q table, 95 confidence level, n equal to 6, so 0.625. So Q experiment is larger than Q critical, so data 10.45 can be rejected. Okay, that is the way to calculate the outlier. Right now, second example, we arrange the data first with the increasing value. The suspected data, Q table from 6 determination, 95 confidence level is 0.625. All right. So where is the outlier? The highest one. So we deduct with the close one. 56.23 minus 56.08 divide, okay, by the same value we got. Sorry, divide by 6. We must divide by the largest minus lowest. Okay. All right, we got 0.1304, and then Q calculated is lower than Q table, so data cannot be rejected. All right. Okay, and more example that you can see from the notes. Okay, that's all for today. I have extra 23 minutes now. You have class after this, or you already go to your class now? Is the T table will given in the question? Yes, it will be given. If the related question asks, we will give the table inside the question paper. Okay, guys. All right. Actually, I would like to have an extra class to discuss about the test and the quiz. Okay. But it is depend on your agreement. Okay. The extra class only just like the tutorial, the preparation for the final exam. The first thing that I need to ask from all of you, are you here now in UTM or not yet? Guys, are you already here in UTM or not yet? Teo Chun Sheng, not yet, not yet. A lot of most of you are not yet here in UTM, but it's okay. When is your first exam?
8 February.
Oh, so 7 February baru nak datang lah ni. Okay. Actually, I will organize, but it's not compulsory. For those who want to come to my class, you can come. Okay, but Rushaidi, are you here, Rushaidi?
Yes, doctor.
Okay, but I hope that Rushaidi can come because I will pass all the papers to Rushaidi. Can Rushaidi?
Can, doctor.
Okay. All right. If it is possible, okay, I would like to do the extra class tonight. Food provided. The dinner provided. And we will do that similar place at C17, DK2. Can come here and we can discuss about the quiz and tests that have been done. And I will pass the question paper, your answer script. And for those who are not coming, I will pass to Rushaidi. So Rushaidi will pass to you guys who are not coming. Can we do that? If can, I would like to decide that we must start at 8:30 p.m. You can come early, 8 p.m. Food provided. You can have your dinner here first before we start the tutorial class. And then during the class, we will discuss about the quiz, about the test, and then if you want to ask other questions that related to the course, also can. And then it should be not so formal class, santai-santai saja. Okay. So I would like to have a survey. How many of you can come to the class for me to book the food? Okay, so that it will not waste there. So Rushaidi, can you have a survey for me? Organize a survey for me.
Yes, Doctor.
Okay, thank you so much. I think that's all for today for our formal class. Guys, thank you so much for uh, your attention, your commitment for the course during the whole semester with me and Dr. Amy. I would like to apologize if there are any mistakes, okay, any what we call that, any not appropriate thing that happened during the class, during the session. I want to apologize, and I hope that you guys can fill in the EPPP for both of us, me and Dr. Amy. Okay, for the final examination, okay, be well prepared. Okay, answer, do exercise. Okay, especially exercise in the notes that have been given. Look at the how they answer in the note, how the question be answered. Okay, and be focused about the thing that we have taught in the class. Recall again. Okay, what is important things that we always stress in the class. Okay. With that, thank you so much. And then for those who want to come tonight, see you tonight. And assalamualaikum and bye bye.
Thank you, Doctor.
Anyone? All right, Samuel. Anyone want to scan the attendance?
Thank you, Doctor. Me, Doctor.
All right, I will open the attendance.
Doctor.
All right. Welcome.
Doctor, just now the survey available at what time? The date
Huh?
and the date and the time for the dinner.
Today, 26 January, the time is 8:30 p.m.
No. The
Huh?
date for the survey. Doctor kata suruh buat survey kan tadi.
Dah survey survey untuk kelas malam ni lah.
Oh, okay.
Survey untuk kelas malam ni. Siapa yang boleh datang lah. So that saya can tempah makanan yang cukup-cukup lah.
Okay.
Okay.
So malam ni ada kelas the Doctor cakap dapat C17.
C17
Okay.
maybe DK2 lah, DK2 C17.
C70 DK tu. Okay.